My name is Gorm Andresen. I'm associate professor at Aarhus University in Denmark, where I study decarbonization of the energy system. In this presentation, I will walk you through one of our recent research papers. A reference to the paper is included at the end of the presentation. I will focus on two different aspects of the paper. First, some of the results, which are concerned with different decarbonization scenarios of the European electricity system, and secondly, a novel methodology called Modeling All Alternatives that we have recently developed in my research group. In the figure above, I have plotted the EU greenhouse gas emissions since 1990, as well as the common EU targets for 2030 and 2050. I have included this figure to highlight the fact that many different sectors contribute to the emissions. I also want to bring your attention to the fact that EU has agreed on common targets. Afterwards, the membership countries have to agree on how to share the effort between each other. And it is by no means given that the effort is shared evenly. It is the outcome of these different effort-sharing scenarios that is the topic of the research. Although all sectors can and should contribute to reach the common emission targets, our study focuses on the electricity sector, seen in blue above. We also zoom in on the 2030 target of 55% emission reductions. These choices have been made to simplify the study case because the modeling all alternatives methodology can be very computationally demanding. However, we still think that the results are relevant because the electricity sector is envisioned to play a key role in the decarbonization strategy. In addition, the limited time before 2030 will most likely mean that the amount of sector integration that can be implemented at European level is limited. However, I want to emphasize that the sector integration is a powerful tool to achieve deep decarbonization, and it should be implemented as fast as possible. The main tool of our study is a techno-economic energy system model of the European electricity network in 2030. We use the open source model PIPESA-EUROSEC with brownfield capacities. This means that existing infrastructure such as power plants and transmission lines are accounted for. On the picture you can see the different technologies that we include. For instance, we have wind, solar, hydro and nuclear power, as well as various fossil fuel technologies. In total, we include 11 different generator technologies and 3 storage types. Grid capacities are aligned with the 10-year network development plan of ENTSO-E. Our baseline scenario is the outcome of a standard cost optimization where we impose the 55% reduction target and demand that electricity is supplied all 8,760 hours of the year with the lowest annualized cost. But we did not stop at the baseline. In fact, we include an additional 30,000 simulations to explore different ways of distributing the emission rights between the countries. But before I dive into these results, I have included a short discussion of the effort sharing. Decarbonization effort can be shared in many ways. Some of the most common principles are listed in the table shown here. First, we have grandfathering, where the right to emit is based on historical emissions. This principle recognizes that it may be extra difficult for large emitters to reach low absolute emissions, but it can also be seen as unfair because countries with high historical emissions carry a greater responsibility for the climate crisis. The principles of sovereignty and egalitarianism distributes the rights to emit more evenly, either according to total energy demand of the country or according to the country's population size. Similarly, the ability to pay principle distributes the emissions such that the wealthy countries contribute more to emission target reductions. Finally, the efficiency principle seeks to maximize global welfare by reducing the total cost of the entire system. This principle is the same as the baseline scenario of our study. However, many other schemes and combinations of schemes can be argued for. In our study, we wanted to explore all of the possible schemes and quantify the total economic performance of the schemes, the emission performance, and national performance in terms of, for instance, abatement costs or electricity price for the individual countries. This is where modeling all alternatives comes into play. Modeling all alternatives involves complex mathematics, but the concept can be relatively easily understood. Our baseline scenario represents the cost of an optimal solution to the effort sharing problem. This can be compared to finding the single lowest point in a landscape. However, our model may be somewhat wrong, and we know for a fact that many solutions with very similar costs can be found close to the optimal solution. So instead of looking for a single point, we try to identify the so-called near-optimal space. In the landscape analogy, this would correspond to finding the small lake in the valley. As pointed out first by Professor Brill in 1979 and later reiterated for energy systems in 2011 by Professor Di Carolis, the relevant real-world solutions are better represented using the near-optimal space, even if it's more complicated. In the study here, we have implemented the modeling all alternatives method with an adaptive metropolis Hastings algorithm. This algorithm works well because of the original optimization problem being both convex and bounded, and it also has the advantage that it is efficient to explore the more than 30 dimensions of the problem. I will not go into the details of the algorithm, but the method ensures that we sample the entire multidimensional solution space evenly and unbiased. Using the method, we have generated 30,000 different effort sharing scenarios. We do this by assigning a random emission right to each country. Afterwards, we optimize the entire European system, and it may turn out that some countries find it optimal not to use all of their rights. We then filter the solutions such that we only look at those relevant for a total emission reduction of at least 55% for the entire European Union. The results are summarized in this figure, where we see that the cost will generally increase for large emission reductions. The line below represents the most efficient solutions, and no solution can exist below this line. But by far, most solutions lie about 5 percentage points above this line. This indicates that the standard solutions to an energy system optimization problem is very particular and most likely underestimates the cost of a real-world solution. The dark blue area indicates locations where most of the possible solutions to the problem can be found. I consider these to be more realistic. If we dive into the country-specific results, we see that nearly all countries experience an increased abatement cost as the emissions approach zero. Some face very high abatement costs, while others see a more modest increase. This is largely due to a combination of existing power plant capacities and renewable energy potentials. For instance, a country like Poland, the lower left, with a large fleet of fossil fuel plants and a modest renewable energy potential, struggle to realize large reductions. Whereas Spain, for instance, on the upper right, has much more promising renewable energy potentials and a more favorable portfolio of power plants that, for instance, includes a reasonable amount of hydropower. This is also reflected in the country-specific CO2 emissions shown here. Here, scenarios where countries like Poland on the far right reach zero emissions may be identified, but the vast majority of scenarios that comply with the common EU goal see relatively high emissions from Poland. Other countries on the far left find it optimal to have near zero emissions in nearly all scenarios. These countries typically have either hydropower or existing nuclear power plants. I hope you enjoyed diving into our recent research. and if you want to read more, please follow the link to the journal paper. Before I finish, I would like to give a special thanks to Tim Tørnes Pedersen. By far, he did most of the hard work behind this study. Also thanks to my co-workers Michael Skov and Marta Victoria for their contributions. Finally, I would like to thank you for listening.